Google's Willow quantum chip has achieved a result that sounds almost unbelievable. In a benchmark designed to test quantum computing, it completed a calculation in just a few minutes, something that researchers estimated would take a leading classical supercomputer an unimaginably long time. That comparison is so extreme that it raises a deeper question. How can a relatively small quantum processor handle a computational space that becomes practically impossible for classical machines? Willow is a 105-qubit quantum processor. Unlike the ordinary bits used by classical computers, which represent information as either 0 or 1, quantum bits can exist in combinations of states through a property called superposition. Qubits can also become entangled, creating connections between quantum states that have no simple classical equivalent. By controlling these effects, quantum computers can explore and manipulate enormous numbers of possible states as part of a single calculation. Willow was tested using a benchmark known as random circuit sampling. The task is extremely difficult for conventional computers because the number of possible quantum states grows incredibly quickly as more qubits are involved. This is why the reported performance attracted so much attention. Google said Willow completed the benchmark in less than 5 minutes, while estimating that a classical supercomputer would require around 10 septillion years to perform the same task using the methods considered in the comparison. However, there is an important distinction. This does not mean Willow is suddenly capable of solving every problem billions or trillions of times faster than today's computers. Random circuit sampling is a specialized benchmark. It demonstrates quantum computational capability, but it is not the same as solving a practical problem such as discovering a new medicine or predicting an entire climate system. The truly fascinating part begins when we ask what quantum computation actually means. Quantum mechanics allows physical systems to behave in ways that seem completely different from ordinary experience. Before measurement, a quantum system can be described as a combination of possible states. When a measurement is made, we observe a particular outcome. Physicists have debated what this means for decades. One interpretation treats quantum possibilities primarily as part of the mathematical description used to predict experimental results. Another famous interpretation, known as the many worlds interpretation, proposes that different possible outcomes correspond to different branches of reality. According to that idea, when a quantum event has multiple possible outcomes, reality does not necessarily choose one outcome and eliminate the others. Instead, every possible outcome could continue in a separate branch. This leads to an extraordinary thought experiment. If a quantum computer manipulates many possible states during a calculation, could those possibilities somehow correspond to different branches of reality? Some physicists have explored quantum computing from a many worlds perspective. In that interpretation, quantum computation can be described as taking advantage of processes that occur across multiple branches, with interference between quantum possibilities helping produce the final result. But there is an important warning. Willow has not proved that parallel universes exist. It has not detected another Earth, communicated with another universe, or demonstrated that information is being transferred between separate realities. The many worlds interpretation remains an interpretation of quantum mechanics. Other interpretations explain the same experimental results without requiring a collection of parallel universes. So the real achievement of Willow is not evidence that Google has discovered another universe. Its importance lies in demonstrating how much computational complexity quantum systems can manipulate under controlled conditions. There is another part of Willow's development that may be even more important for the future: error correction. Quantum information is extremely fragile. Interactions with the surrounding environment can introduce errors and destroy the delicate quantum states required for computation. Building a useful quantum computer therefore requires more than simply adding more qubits. Researchers need systems that can detect and manage errors while preserving the information needed for calculations. Google's work with Willow demonstrated progress in this area. The goal is to develop quantum systems where increasing the size of the machine does not simply create more errors, but eventually allows increasingly reliable computation. If that challenge can be solved at large scale, the consequences could be enormous. Quantum computers could eventually help researchers simulate complex molecules, investigate new materials, improve certain optimization problems, and explore physical systems that are extremely difficult for classical computers to model. They could also have major implications for cryptography because sufficiently powerful quantum computers could threaten some encryption systems used today. But that future is not here yet. A benchmark result, even an extraordinary one, does not automatically mean that quantum computers are ready to replace classical computers. Practical, fault-tolerant quantum machines remain a major engineering challenge. And this is where Willow becomes The biggest mystery surrounding quantum computing is not simply how fast these machines can calculate. It is how they manage information in the first place. A classical computer processes information through physical states that can be represented as bits. A bit can be 0 or 1. Modern processors contain billions of these tiny switches, allowing them to perform enormous numbers of operations every second. Quantum computers operate differently. A qubit can be prepared in a quantum state that represents a combination of 0 and 1. When many qubits interact, the number of possible states grows incredibly quickly. With just a few qubits, the possibilities are manageable. But as more qubits are added, the mathematical space becomes enormous. This is one reason quantum computing is so difficult to understand using ordinary intuition. Imagine trying to describe every possible configuration of a system. A classical machine may need to represent those possibilities explicitly. A quantum system can encode information within a combined quantum state and manipulate that state using carefully controlled operations. But there is a catch. Quantum computers do not simply calculate every possible answer and then magically reveal the correct one. That is a common misconception. The real power comes from interference. Quantum algorithms are designed so that unwanted possibilities can cancel each other while useful possibilities become more prominent. The challenge is designing the calculation so that the final measurement gives a meaningful result. This makes quantum programming completely different from ordinary programming. Instead of simply telling a machine to check one possibility, then another, researchers create quantum operations that transform the entire quantum state. The process is incredibly delicate. Even tiny disturbances can introduce errors. Heat, electromagnetic interference, vibrations, and interactions with the surrounding environment can disrupt quantum information. This is why quantum computers are often operated under extremely controlled conditions. The challenge becomes even greater when researchers try to scale the technology. Adding more qubits sounds straightforward, but every additional component introduces more opportunities for error. That is why quantum error correction is so important. A useful quantum computer will need to perform long calculations while keeping errors under control. Researchers therefore use many physical qubits to protect information stored in logical qubits. The ultimate goal is fault-tolerant quantum computing. If that goal can be reached, quantum computers could become dramatically more useful. Consider chemistry. Nature itself is quantum mechanical. Molecules, atoms, electrons, and chemical bonds all follow quantum rules. Classical computers can simulate these systems, but the calculations can become extremely difficult as the system grows. A sufficiently powerful quantum computer could potentially simulate certain molecular systems more naturally because it follows the same underlying quantum rules. That could eventually help researchers explore new medicines, catalysts, batteries, and materials. But there is another area where quantum computing has attracted enormous attention: cryptography. Much of today's digital security depends on mathematical problems that are extremely difficult for classical computers to solve. A sufficiently powerful fault-tolerant quantum computer could use specialized algorithms to attack some of these mathematical systems much more efficiently. That is why governments, technology companies, and cybersecurity researchers are already preparing for a future in which quantum-resistant encryption becomes necessary. Still, the most exciting possibilities may be problems we have not even identified yet. Whenever a new type of computing becomes available, researchers discover applications that were difficult to imagine beforehand. Classical computers transformed science, communication, entertainment, and business. Quantum computers may eventually do something similar in areas where classical machines struggle. But we should not confuse potential with present capability. Willow is an important experimental milestone, not a universal supercomputer that has suddenly made every difficult problem easy. The benchmark used to demonstrate its performance was specifically chosen because it is extremely challenging for classical simulation. That makes the result scientifically interesting, but it also means the famous comparison should be interpreted carefully. The claim about millions or septillions of years describes a particular computational task and a particular classical approach. It does not mean a classical computer would need that amount of time to perform every calculation Willow can perform. This distinction matters because quantum computing is still developing. The technology has made remarkable progress, but researchers are still working toward machines that combine large numbers of reliable logical qubits with practical error correction. And this brings us back to the strange question of reality. Quantum mechanics does not behave like the world we experience every day. At everyday scales, objects appear to have definite positions and properties. At the quantum level, nature can be described using probabilities, superposition, and entanglement. The mathematical rules work extraordinarily well. But what those rules